Nice to have you. So, lecture 8. Let's see. What is our mood today? Who is mine? I like to see yours too, so that we kind of have an idea. Can I, please? Your mood today. You can influence. Carter, what's the mood, please?
The mood is good.
Good, yeah? Not so excited, right?
Yeah.
Yeah. But Friday is coming, right? Weekend is coming, so that's consoling. Yeah. Okay, nice to have you all. Today we continue with more potential energy functions and solutions of the Schrödinger equation. So far, what's your favorite potential energy?
Infinite.
Infinite wealth. Wow, that was almost unanimous. Why? Serious.
I like the step.
You like?
I like the step.
You like the step. You were quiet, and now I like step too. Yeah, but almost many others. So, what is the reason for preferring infinite? Well,
Probably easy.
the math is easy, or maybe What else, please?
The wave function, zero.
The wave function turns out nice and normalizable. I totally agree. And yes, but all are useful. That is a nice thing. So for utility, for understanding quantum mechanics, let's do more. I asked you to try and read up and on my slides the finite square well. You will have noticed that the finite square well is like the inverse of the barrier that we already did. Yeah? A little bit like that. Evanescent wave and all that. So today we will tie that together quickly. But the focus today, in terms of working on the board or here, if it works, is another nice one, the harmonic oscillator. And the book solves it in two ways, which shows you how important it is. And I'll also show you how important it is at the molecular level. Atoms, molecules, all the quantum mechanical stuff that we care about are vibrating. They are in oscillatory motion. That Planck solution to absorption by atoms of radiation, that was based on harmonic oscillator. And they only called it simple harmonic oscillator. It's not always the simple case. It does not always obey Hooke's law, but it always has the form that we are going to use, 1/2 kx squared. That's what we want to do today. Okay. So, this is the particle in a box kind of animation to remind us infinite square well. Some people call it particle in a box. This is the classical version A. This is quantum mechanical. It's a good wave function. We solve it. We got it, right? Ground state. Yeah. Second. Blue is, guess what? Blue solution is
Real.
The real.
absolutely correct. Real. And red, imaginary. Remember we had A sine kx. Yeah. Or B cosine kx. Both will work, as I told you. And once you get one, you get the other. You can see nicely. There is something not quantum mechanical about E and F. Who can guess?
Are they not normalized?
Something close to that. Good idea. Not only that they are not normalized, it's back to Millie's point, Millie's example of the word eigen. So you could have solutions that are mathematically accurate, but they are not physically representative of quantum mechanical particles. From the Schrödinger equation, the math is made to focus on a set of solutions that fit the physics. So this is mathematically okay, but they are not eigenvalues of the energy. They are not eigenstates of this particle in the box. Yeah. Because, for example, they will not be orthogonal or orthonormal if normalized, for instance. Yeah. So they will not represent quantum mechanical particles. The math is okay, you can solve, you can get, but you want to get a set of solutions that represent the math. So just a flashback before we continue. Not much to say here, just that you try to check the blue line site the moment the lecture is over, because, for instance, last lecture was there. So how many went to it already? Very good, because I wanted you to read and prepare for the lecture, since I have the finite square well right there. So that's a finite square well. We will return to my slides after we get into the simple harmonic or the harmonic oscillator on the board. Is that okay? And we'll do two exercises, one on the properties of the solutions to finite square well, and the other one, of course, harmonic oscillator. All right, so last time we tried, it didn't. Let's see if we can get this to work. Any questions so far? Okay, so you permit me to try it here first and see if it works, and then we can continue. Let me not show on the screen something that is not what we're doing on the board. So on the screen, I'll prefer to show this one as the exercise we will handle. So I prefer to show the harmonic oscillator. Yeah, one-dimensional. All right, so let's do it. I wanted to say the diagram is already there. Since it is not there, let us do something. This would be 20 what, please?
Should we put the finite square well as 23?
So this would be 23.
Yeah.
Well, is the finite square well 23?
22 is finite square well. And
22 is infinite square well.
Oh, infinite square well.
Over
Okay,
finite
so
square well.
let's focus on we do together on the board, which I will hold you more responsible for. So 22 was infinite square well. So let 23 be the harmonic oscillator. Thank you. So 23. Let's call it quantum harmonic oscillator. And I can begin to draw it sort of, if it lets me, something like that. Yeah, we can do something like that, and we can have our X right there, okay? And we can draw here at any point, maybe B, and call it V of X. So, that's what we usually do. We kind of sketch it, and maybe to connect. Since I keep catching myself saying simple harmonic oscillator, let's differentiate them. Is that okay? So, of course, I will say A starts simple harmonic motion. That's F equals negative Kx. You remember that, right? So, simple harmonic motion classically is when the force obeys Hooke's law. Only small displacement. Just reminder. But we want something a bit more general. Of course, we can solve this. This is MA equals negative Kx, right? What's the solution? M d squared x dt squared equals what? Negative Kx. So what is the solution there? Quick one, just reminder. Yeah, so x of t then equals a sine what?
Kx.
How about omega t? Yeah? Yeah? plus B cosine omega t. Yeah? Just to remind you where this omega comes from. Omega is what in this case?
Root K.
Sorry?
Is it root K?
Yes, square root of
K over M.
K over M. And that means omega squared is K over M. And what is this K here? Is that the wave number? No. What is it? The spring constant. So just a reminder, to make it more general, beyond Hooke's law kind of thing, I can write here Hooke's law. So beyond the Hooke's law part, which easily breaks down, we can expand more general, so Taylor expansion of any oscillatory behavior can be done. Not just the one that obeys Hooke's law. Is that okay? So what is the Taylor expansion that we can do for a general potential energy that is oscillating about a point like this? What's the Taylor expansion? Something we do a lot as physicists. So V of x will then be approximately, let's expand it around B. What will then be the first term, please? VB, right? So the zeroth term, let's call it that, the zeroth term. Then the first term will be V prime. B minus x, right? VB, and then let me write it in a way familiar to most of you from the way I'm looking. So VB into x minus B prime, yeah, plus what? 1/2 completed.
V double prime V.
Excellent. V double prime. So VB double prime into
X minus B.
X minus B squared. Yeah, and we can have other terms. So this is arbitrary. We can take this to be the origin, so 0. The first derivative, as we go a little x away from B, the first derivative is what? Very little. So at the point B, we're expanding at point B. What is the first derivative there? 0. Yeah, 0, 0. Yeah, so 0 here. And what survives is the second order term. The third order would be a lot. Tiny. So that's the point. So in general, you know this. I'm reminding you. Equals this guy times x squared. Yeah? So we can call this guy, the second derivative there, the second order term, we can call it alpha 1/2. Usually it is kx squared, which we call in our case 1/2 alpha x squared. The reason I do that is because I don't want to confuse myself over k as spring constant here and k as wave number. Are we okay? Any question? All right, so let's write down our potential for the quantum harmonic oscillator. So V, finally, will then be, in terms of, let's write what this alpha or k actually denotes. We said here that omega is square root of k over m. In our solution general coming from the Taylor expansion, that will be square root of alpha over m. So what is omega squared? Help me. Omega squared equals alpha over m. So our alpha is what? What is our alpha?
Omega squared.
M omega squared. So we can put it right there. V equals 1/2 alpha, which is m omega squared x squared. That's what we will be working with. Seen that before, right? When solving? Yes. It expresses it as a function of x with a constant what? Angular frequency, which is good. So we've got our step 1 v. Yeah, so our step 1, you can call it a step for getting v of x. Let's do step 2. Time independent Schrödinger equation. Yeah, you could have suspected that. So what is a time independent Schrödinger equation? I told you. You'll be so tired of writing it. H bar squared over 2m d squared psi dx squared plus what? V of x psi of x equals e psi. Now we do our usual thing and get psi double prime to stay by itself. What will that look like? Psi double prime will then be equal to negative h bar. Oh no, let's put it this way. So negative 2m over h bar squared into what? I'm dividing everything by 2, negative 2m over h bar squared. So I got rid of this one and I sent this one over here into e, so the v here becomes minus psi. Check if that is correct. Carter says yes. Yeah, Tucker says yes. Who else? Alan says yes. Who else? Yeah, everyone. Okay. Melanie, do you agree? I didn't. Is it okay? All right. So let's bring it over here. Oh, I said it. So we are doing our step 2, which is time independent Schrödinger equation. Okay. Just so that your revision and following can be a little bit more smooth. Can I then wipe this so that we check what it is? Okay. So, seems the manual is faster. I don't want to wipe everything, but half of it. Let's not forget our expression right there for v, but we'll put it in shortly. That looks good. Can we take that into the left-hand side and make it 0 and try to solve? Okay. So, continuing our step 2, time-independent Schrödinger equation. We've got our psi double prime plus 2m over h bar squared into e minus v psi of x equals 0. Looks like something we can solve. If only v were a constant. Do you remember with those steps and barriers? V were constant and it was just easy. But now v is not a constant but a function. So we have to rearrange it and put the explicit form of v. Okay? So that allows us to say, well, psi double prime plus 2m e. I'm going to write it out this way. 2m e over h bar squared minus 2m v over h bar squared psi of x equals 0. So, psi double prime plus, I still keep my 2me over h bar squared minus. Now we have our 2m. What's the explicit form of v? Right there. So you plug it in and tell me what this term becomes. Everybody. Plug in this expression 1/2 m omega squared x squared into v here. And what do we have? Who's ready?
So that whole term becomes omega squared x squared over h bar squared.
So minus what?
So minus omega squared x squared over h bar squared.
What happened to the m?
The m. Oh wait, sorry. M
Anybody? Yeah? Done? Yes, please cut that.
Negative, or I guess minus m squared alpha omega squared over
M
h bar
squared. But we've already put in alpha, so there's no alpha.
Oh, yeah.
That's the alpha right there. And that's why I wanted to do it, so that everything is transparent. So m squared, anybody?
Omega squared x
Omega
squared
squared. X squared.
over h bar squared. Over h bar.
So divided by h bar squared psi of x equals 0. Are we okay with that? Everyone happy? That is what we want to solve, and it can be solved. It can be done analytically, which unfortunately our textbook author, an author I respect, Griffiths, says is brute force. But it is analytic and it is correct, and he likes it. He gives a solution though. He has another nice way of solving it, which we will do perhaps in 2 weeks using ladder operators. How did he describe it? He described it in a very interesting way. Anybody remembers? Did you read the book? So how did he describe the second method there? So the first method he mentioned was, well, you can do it analytically, and it is brute force. And the only reason you call this brute force is because of the algebraic method, because it's more elegant. And that is what makes the analytic, which we're going to do, to appear brute or brutal. It's not that brutal, it's kind of fine. And it's what many physicists are already familiar with. So how did he describe it? The algebraic method. He said the method is what? I'm checking your reading. Griffiths uses words like that and gets away with it, and it is very effective. So I'm like,
Diabolically clever.
Say it out loud. That is the word expression.
Diabolically clever.
Diabolically clever. You see what you are missing if you are not reading. He says the algebraic method is diabolically clever. Read. All right. So we'll do the algebraic method after we have studied operators. And we will study operators from next week. Is that okay? So get ready. Now let's use what he calls brute force, which is more the normal way physicists approach differential equations, partial or ordinary. That was a good break for you, okay? Now you see you're missing things if you're not reading. So, guess the next thing to do. Now that we have this equation. Yeah, let's call it step 3. Let's do it together. Render dimensionless for easy solution. How can we render this equation dimensionless? Are we together? How? Can we do it? I heard some.
Elaborate.
Rewrite the terms. The terms that are changing, the x and maybe the energy. Write terms that have energy. So I'm going to clean this part. Oh my God. Yeah, we know the potential, so I can take that space. Okay. So let's rewrite. We are on step 3, render dimensionless. How? Let's start with this one so that you can check. A certain epsilon. I prefer epsilon. I think the book uses something else. B 2e over h bar omega. Check. Is that dimensionless? Is it?
Yes.
What is the unit of energy? Okay. And what is the unit of h bar omega?
Joule seconds or EV seconds.
Sorry?
Joule time seconds.
That is the unit of h bar only.
Oh, H bar, yeah. H bar omega.
That's what I'm checking.
Yeah, and then times omega is
Yes.
just joules.
Very good. So you now agree that that is dimensionless?
Yeah.
Very good. So let epsilon be that. And let Q be x into square root of m omega h bar. And you can check as exercise if that is also dimensionless. You will need to use h bar as joule seconds to get all that so that you convince yourself that it is also dimensionless. It is. Okay? We've checked the first, you can later check the second. And if you apply that to this equation, what are you going to get? So this is check for you if it works. So render dimensionless. And that should give us psi double prime plus epsilon. This is our new epsilon minus q squared into psi. Now a function of q equals 0. The reason is to make the solution easy. To make the solution pop out. Because we've arranged it in a form that we already know how to solve. Any question? Put in epsilon, put in q squared, and check if you get back this.
Does q squared work? Because if you square it, then you're not going to have m squared, omega squared, or h bar.
Have you done it already? Do it on paper and check.
If you square q, you won't have m squared, omega squared, or h bar. It'll just be m omega h bar.
Would be x squared m omega over h bar.
Yes, but then you have made this. So whatever was x squared, yeah, is what you've now changed to q squared. So if you do it that way, you will see that it works. Change it that way because things cancel out. That you are left with things downstairs.
Write it out because
Yeah.
I'm not understanding.
So check it as
Well,
exercise.
If you square q,
Mhm.
then it's going to be x squared times m omega over h bar.
But you've got only, watch it now. Watch it. Good point. Good point. Really good point. His question is very important, so I'm pausing to acknowledge it and so that it will help you all check it. And that's exactly how I want you to follow steps. Don't agree with me if it doesn't make sense. So I like that, okay? I really do. Look, changing it is about changing the whole of this and not just this. So you did a good job quickly trying to change to see if you get q squared here. But this is not e. You got it now. This is not epsilon. Watch it again. Watch my answer. Watch my immediate response. This is not epsilon. You are just assuming, okay, epsilon, this doesn't give me q squared. Do you agree with me now?
Yes.
Yes. If you can make this epsilon, you are going to get q squared there. And it takes a little bit of time, and I want you to do it when you're cooler. Are we together? You got it now? Can I repeat my answer to him? He quickly tried to check to get q squared here, which is not q squared. But that's because this is not epsilon squared.
Makes sense.
Yes, please.
So in the first term, only a part of it is epsilon.
I'm sorry?
So in the first term, only a part of it is epsilon, right?
Yes, see, we've rearranged things so that this is epsilon. So it takes a few steps, a number of steps, to show that this epsilon, if it replaces this, then what follows will be q squared. So you cannot just say, hey, I've got epsilon there. It's not epsilon. You have to rewrite the whole thing to get epsilon minus q squared. So once again, summary, watch my hands, please, everyone. We want everything in the bracket to become epsilon minus q squared. Do that. You got it. And we continue. Yeah? Because it's just a little bit algebra. Good point. Let's continue. We've got the dimensionless form, which is very interesting because it has been solved before. Who knows what the solution entails? Equations of this form have been solved before. Anybody?
Quadratic.
Sorry? Anybody? Hermit equation? Anybody seen it before? This is a form that leads to Hermit equation. This form leads to Hermit equations. Guess what? Can I tell you something? Can I tell you something?
Yes.
Quantum mechanics hands on operators being Hermitian, so we better take him seriously. Hermiticity of a quantum mechanical operator is the sine qua non for it giving us eigenvalues we want. So we are connecting ourselves with good math. Okay? So this equation can be solved as a form that leads to Hermit polynomial. Okay? And being Hermitian is a big deal. So let's do that. One quick way to do it is to take limits. Yeah? So solution entails all that. Solution, lots of steps, but we can summarize it quickly. I have the details on my slides, which we will go through together, but let's summarize it on the board, first of all. Think about it. When Q, which contains X, can you see my hands, please? When Q, which contains X, gets very large, because those are the limits we like to take. Limits. Q goes to infinity, maybe, or very large. Very large. What might the solution look like? What happens to the term epsilon? Negligible. Very good. You got it. And let me go with that. So you just told me that psi double prime is approximately q squared psi of q. Q very large. That's what you just told me, and you are correct. And the moment we see that a second derivative is back to itself with a square term right there, we can guess the solution. It means that the solution is of the form e to negative q squared over 2 immediately. Yeah? Because of this behavior. So we now have an idea of the solution at very large q. That's good. Let's go further quickly. We will soon land. That gives you time to think a little bit.
Is that then that psi equals e to the negative q squared over 2?
About that.
I think that's what's
Because, so the exponential, Q really big, Q going very large, so like X, this should go close to 0. And it does that because there is a Q squared right there. Otherwise, it will just be an ordinary decaying exponential. Does that make sense? Yeah. So it behaves well as we expect, even physically, for a wave function. Yes, please.
How come it's over 2?
Yeah, that's largely based on symmetry of the problem.
Okay.
Yeah. It wouldn't, good point. It wouldn't change the solution if it is just Q squared. Yeah. Because Q is very, I like these questions. Yeah. At that level, negative Q squared is negative Q. Sorry, negative Q squared over 2 is negative Q squared. For Q very large as we want. Are we okay with that? Good. Nice. Any other question, please? I really like these questions. Okay. So we've got the nature of the solution for large Q. And it seems to behave well in terms of quantum mechanical wave functions that should go to what? At infinite x. What should they go to? 0. Yeah. So without wasting your time, I tell you the next step in the solution. It will be power series. Who has ever done a power series solution? Anybody, please? Power series solution. Very good. Yeah, I have the details on my slide. So I can wrap up the board 1 so that we look at this detailed power series solution. But what? Yes, Carter?
So whenever we're learning how to solve these and stuff, I assume that the details on the board are helpful, but that's not what we're focusing on. We're focusing on what we write up here, right?
What you are focusing on what?
I guess just when we're taking a test in the future, we don't need to worry about the details on your slides, more so these types of solutions.
Correct.
Awesome.
Because I've said so earlier.
Yeah, I just wanted to make sure again.
You're correct. So we do the physics a lot on the board and the summary of those math details. Is that okay? So no scare, nothing scary.
Yes.
Yes.
Very good.
And that's why I'm so pleased that you understand the details on the board. If not, if we use all the things on the slide, we get blocked with the tools and not the results. So good repeat. Thank you. All right. So the power series, which is details, which is done in a full course elsewhere, right? We apply it, and I also go to the trouble of showing you those details on my slide. But let's use it here. The power series ends up imposing conditions on epsilon. Conditions that are very interesting. So here we have epsilon equals 2e over h bar omega. It turns out that through the power series method, the epsilon ends up, the solution to the power series requires epsilon to be simply this. Wow. And that is the gist, because that gives us our energy. And in that power series, the n will be 0, 1, 2, integers beginning from 0. And what will the wave function itself be? Well, the wave function ends up being quantized. It will be some constant and the Hermite polynomials. And what we already knew of the solution, negative q squared over 2. This is what we're going to get from the power series solution for the wave function. And to conclude this part, this board part, this big physics summary part on the board, you're going to tell me now what E will have to be based on the power series solution requirement for epsilon. So you're going to tell me En now. Hey, hey, hey. There's a sweet part for you. Do it on your paper and tell me, yeah? What will it be?
It would just be 1/2 plus n times h bar omega.
So what will it be? 1/2?
1/2 plus n, and then all times h bar omega.
That's a nice way to put it. That's one way to put it. Yeah? You agree? That's a nice way to put it. Who else has put it in a different way? So we can solve it even explicitly and say, okay, so 2E equals h bar omega 1 plus that. So En equals, so we've got our h bar omega, yeah? And then we can put the 1/2 up front here. And what else do we have? So we've got our 2E over h bar. The h bar omega gets out there. Okay? So if we put the h bar here, omega, how can we handle that? It makes it a little bit difficult. I like this nice, easy way of putting it. Yeah? So this works nicely. And you can also have the 1/2 and put it in there, okay? So let's have the 1/2 over there, and we'll end up with h bar omega, and what will be inside here? Sorry?
1 plus 2.
1 plus 2.
We happy? Different ways of doing the same thing. So which one did you do? First one or second one? You did first one? Very good. First one? Second one? Nice! Cool. So let's talk about it. What does it say about the ground state energy of the harmonic oscillator when n is 0? When n is 0, the energy is
1/2 h bar.
1/2 omega. You got it. When n is 1, yeah, then 3/2 omega. Oh, those are the energies, the eigen energies of the quantum harmonic oscillator. Good job. And that comes from our expression for dimensionless, for expressing the equation dimensionless, having the imposed quantization on it due to the power series method of solving it. And the power series method of solving it, in this case, uses Hermite equation. And I have those on my slides. And it should be reminders if you've done it before. And this is not the class for doing it for the first time, because it makes the math to get into the way of the physics. Is that okay? And I am doing it this way so that if you've not done it before, you're not at a big disadvantage. You have a way to find it. And you still do quantum physics. Is that okay? That's my strategy. Otherwise, we will then digress into all this power series, polynomials, Hermite polynomials, and then we will get lost or lose sight of the physics. There's not time for that. Okay, so I give 2 minutes break, and we get to the math details on the slides, okay?
Recursion. Oh, I wrote that out. So that's the size. That's the second.
Oh shoot! I'm just too bad.
There's two ways to think about it.
There's that way where
yes, it'll be tough studying for both,
This is how we solve for E.
but at the
What about the
same
negative?
time,
did
that
the
means
you won't
Yes, we don't.
homeworks might be graded.
Just wait
This
for
is
the
You will
solution.
not have to work on
What
one
if this
of the other
is
homeworks we're all supposed to be studying for the exam.
This is a constant.
And
That's
then your brain's just gonna be
It's just a big fault. It's a power series.
Okay. Wait, is this the same thing that we did?
it's either like
Is that the same list of equations that we have?
I feel like it's gonna be better because there's
Okay, so this is just one of
won't be
these.
as the
Well,
Oh,
it's the
we should
end.
have one of yes, and like we had
It's basically right
a list
afterwards.
of them.
Whereas
Okay,
you
well,
know,
that kinda makes
if it was on
sense.
Thursday, you get
A
an
and
entire
it's just a,
weekend to be like, man,
it's usually like
It's a series
A
solution,
goes
so it's not just
So
one
that's
thing.
like-
It's a full series.
That's how you normalize it to A's, right?
Like,
Yeah.
we've gone through everything so quickly. I
Remember
just,
that
I don't know.
class, or wait.
Like we keep talking about.
I'm not remember that.
She had this giant list of equations that I went to all the time.
Like sounds vaguely familiar, but
Okay, I can look up, and as soon as I show you, you'll be like, oh, I definitely remember that.
well, it's just a bunch of polynomials.
Yeah.
Oh, also, I forgot. How do you get to?
He watched me struggle through
How
that
do you get
first
to this
homework
equation?
because I did figure it in his office.
Yeah, I did over.
You just take the in version of this and plug it in.
Did not enforce it.
This,
Like, I never
Like,
did
how do you know
I
this
don't
is
want
the
to
solution for this?
I found the directions, I have no idea.
just
It's like, it looks like this, but
that's
I don't know what the pictures are.
Well, you know that that's what I'll think.
Yeah.
So well,
You can like split it up.
the way that I have it, like here, like I have the second derivative.
Alright, so what was that?
You divide that, it's the same thing.
Can we continue?
We just kind of figure out what's better.
Yeah, but if you take the derivative of this.
Any question? Can we continue? So we have the expansion, the Taylor expansion, and so we have this expression which we did on the board, and let's take it further. We also have this one, and remember you have to confirm that this is correct, okay? So confirm that for yourself, it is. And now the Hermite equation. What does the Hermite equation do? Is anybody worried about the homework that is due tonight? If that is getting into the way of the lecture, that's not okay. Because then you miss what is needed for further work, right? So here, when V is very much larger than E, which means V going very, very large, we end up with that expression, which is approximately E to the negative Q squared, but it's easier to have it as E to the negative Q squared over 2 in view of making use of the Hermite equation, making use of the already known solution to the Hermite equation. It's almost like somebody knowing the solution to Newton's equation and rendering their equation to be in that form so that they use that solution. That's what we're doing here. So that's the Hermite equation based on this substitution and expression. So function of x is now function of q, and q is dimensionless, which makes it easy to do the power series method. And if you've not done the power series method before, well, this is your first chance. How many have done power series? Very good. So this is almost like Taylor expansion, but you have steps that are integers. So any function can be expanded in a power series. You know that, right? Any function. It's a powerful analytic way of solving stuff. So this is just a smart way of expanding it such that you end up with everything in terms of r from 0 to infinity, little bits of it, integers. And then substituting that power series into the Hermite equation, we end up with that. What is that Hermite equation again? I show you on the slide. That's it there. So you've expressed your h of q in terms of a power series, put it back into the Hermite equation, and you're almost there with the solution. All you need to do is rearrange stuff to get what is usually called a recursion formula. A formula that allows you to get the terms as your n or r increases from 1 to 2, 3. That's what it's called a recursion formula. And that's the recursion formula, right? Okay? And r is like our n. I'm just not using n so that we don't confuse it. Later on, we will put in r as n. Oh, it's already there. Yeah. So that's the recursion formula. Most books use n already, but I just wanted to start with something general and put it. So, the constraint comes in power series at those limits. What happens at the limits? Is your expansion diverging or converging? That's the usual question, right? So, it diverges if you have 2q squared or 3q squared, etc. That's the divergence. And so that's what kicks out those kind of solutions and leaves us only with this. Yeah? So with that avoidance of divergence, we can take the expression for the recursion formula and render it in a form that prevents that divergence. And that form is right there. The energy must be such that, see, the energy, because the energy is related to epsilon, this term must end up being 0. Remember, r is your n. So if you solve here, you then have epsilon must be equal to 1 plus 2n. That's the key point of the solution, coming from the recursion relation and the need to avoid divergence. Okay? So, applying that to E equals 2n plus 1, we end up with what we had already together. For the energy and the ground state energy, 1/2 omega, and our wave function in terms of Hermite polynomials. This is extremely easy if you've ever solved power series with Hermite polynomial. Admittedly, this is not super easy if you've never done it, but that is the tool we use to get this solution. So it's up to us to decide whether to focus on the details of how the car works or whether to use the car from Omaha to Lincoln. We just use the car from Omaha to Lincoln. Is that okay? That's what I will admit that that's what we've done. We can then figure out how the car works in perhaps another class because it's so cool. I would love to teach advanced math, but that's not what I'm teaching. So, what are the properties? And these are the kind of things that show up in the exam. It is true that you are responsible for what we did on the board, but there are some things on the slides that make clear what we did on the board. Is that okay? For example, the ground state energy, look at what it is. And I can ask what the ground state energy would be. I can ask things like, what is the spacing? And this shows up from the recursion formula. Does that make sense? Every n is a step further. It's integer. Moving. And what is the nature of the solution? Is this even? Is the ground state even or odd?
Even.
Even. Very good.
Even.
Exactly. And you can see it there. And the fancy word for that is parity, which is why I try to explain in terms of the physics. Parity is cool in terms of the physics beyond even the math. It's real. There's conservation of parity. So, a little bit of what happens when you use the same idea in the case of tiny molecules that are vibrating with energy that is given by the thermal energy at the molecular level. So, atoms, molecules. What's the approximate speed of molecules in the atmosphere as we are now?
5.
Average molecular speed is about
500 meters per second.
500 meters per second, yeah. So we know the average kinetic energy, and that average kinetic energy is close to that in terms of temperature. It's a connection between speed and temperature, yeah, using the Boltzmann constant. So now we've done the connection, thermal and kinetic. We can see how eventually Planck used quantum mechanics to solve and explain absorption and emission of radiation. He assumed that stuff is behaving in terms of harmonic oscillator. So basically, Planck had the solution. His assumption was that the molecules are behaving like oscillators, and he assumed that the energies are quantized. So he basically assumed the solution to the quantum harmonic oscillator and applied that to his expression for vibrational energy per molecule. And using that expression, fitted to the result, fitted to the model, so experimental result. This is what it gave him for the thermal process, and that fitting ended up being the distribution that is also experimentally obtained. The expression that avoids ultraviolet catastrophe. This is just connecting with what we've done before. Okay? So it worked. Again, Planck used oscillator solution to fit and get that. So it was a proof of quantization at the level of vibration, at the level of stuff, absorbing radiation and getting more energy to vibrate more. Stuff radiating because they've got more energy. How are they radiating? Because they're now vibrating more. How are they vibrating? Like oscillators. Yeah, about a fixed position, the solution. So these are more experimental things that you can read if you're already familiar with thermal physics. We will get back to this slide towards chapter 5. So don't bother about it, but we'll use it in chapter 5. That's when we'll be talking about rotational kinetic energy and all that. So I'm pausing so that you get ready to do the exercise 1. So after this, we will do a quick one on the finite square well and also answer a question similar to this. So go through it. Is anything blocked? If something is blocked, you can look at this one. So discuss with each other. Group work. Which group? I need to see the group and your group solution.
Okay.
So which group is ready?
Not yet.
So you can look here if here is blocked.
Because the first excited it goes through. It goes through.
First excited state looks like that.
So yeah.
I think it's.
Yeah.
Oh, I guess you're right.
Sorry, I just finished it. I was reading the question.
Which means
2 is.
I don't understand what
You remember when I showed those graphs? What is probability? Psi squared, right? And I focus on what psi looks like at ground state. I kept doing all that and saying, hey, Stop thinking homework. Let's work together. Here it is.
Number 3 is not right.
You will never find
And you're probably finding it outside is not zero. Did you tunnel?
You have an evidence.
Wait, so that would
That 3 is not right. I don't know about 1, I'm gonna read
I
wrong.
mean, one is contrary. So,
Yeah, you have the wave there, but like you'll never find it there.
So it has to be past the boundary in order for you to
Think through, make sure you go through every of the 3 options and convince yourself. Then convince your neighbor. I've given enough time for it.
Yeah.
Why is number 2 right? They're probably finding the one vertically centered.
Joey said,
Is
like,
the
the first example,
the first example is oh yeah, it crosses the
Yeah,
ground.
it's
I
actually
should really
saying one,
read
it's
this.
saying it is most likely found in the center, it's not like
Yeah, that's
Yeah.
so
Yeah.
everything. So I think
Yeah.
one is
Yeah.
wrong, 2 is right, I don't
Twos, right?
I don't see how.
Why not 3?
This is the physics.
Like, to me, it's the trick question.
Yeah.
It's
Really?
Which state is it talking about in number 1?
Maybe a
This
choice.
is classically the particle has the highest probability of
More or
finding it.
less.
That's a
Good.
trick question.
Go for it,
For the
please.
ground state. Oh
ground
shoot,
Give
wait,
us your
no.
answer. Give us
That
give
one
your
would be
answer
right.
for the ground state.
Okay.
1 and 2, right? I think C.
Don't wait for the answer. Be passionate about your answer. Then it will make sense when we get the answer. If not, it's another wasted period for you.
So 2
because you can go D.
Because
Say E.
You said E.
E.
What if it's
All of them go.
We say C with absolute confidence.
Did you hear that, everybody? What's the reason for your confidence?
Because you told us to be confident.
I like that. This makes it lighter. People are now smiling. This is what I want. So I've heard from this group, this group, this group. Are you in the contact group? Okay, let's call it the Melanie group.
I like that.
Yes.
She runs
So
this
we
place.
want to make Melanie speak. So Melanie, your group said what?
We said C.
C. She has the same confidence as the group. Oh, okay. What is yours, please?
We
said E.
Yeah, that's what we say.
Yeah.
3 is saying it finds
Millie, what did you say? Which group? Yeah.
With them, yeah.
This is actually very good. So the class, it's C. Okay? The class actually agrees 1 and 2. Everyone sees 1 and 2 as correct. That's good. So the trick was how to eliminate 3.
Is it because the tunneling exists?
Yes, a little bit of it.
Isn't it?
We didn't impose that condition in the solution. In the solution, remember, the potential energy could really be big and things will still work. Q, getting very big, is being really bigger than E. Yeah? You could have a very huge potential, and so the probability of finding it in the regions where the E of the is less. So it's almost always less, if you like. You can make
It's 0.
V very big. Remember, we had a solution in which Q went the wave function, and the solution was good in spite of that. Yes.
Isn't it technically a non-physical result though, because there's no barrier for it to pass through? So in order for the tunneling to happen, there has to be like an empty space on the other side, or at least a space where the energy will still be the same. So it can actually tunnel through and then have a wave on the other side.
Good point. So in tunneling, you are looking at 2 things: tunneling through versus being found in a region that it shouldn't be there
Yeah, I
classically.
know. This is
Yeah.
weird.
So this is
The difference
basically
is the step
being
function
found in a
versus-
region that it should not be there classically.
Got it.
If the barrier thickness is small, then
You're right, when
Then we
E is
get
less than 3, we get the decay.
yes. So good job. 1 and 2, correct, right? And 3 is a condition we did not impose on that solution. V can be really big and we still have our particle doing its quantum mechanical stuff. Okay? So good job. I'm happy with that. But take notes then that that condition is not needed. 3. Okay? So Another thing that is more like, okay, if they are interested. We just did one dimension, right? Yeah. So you decide what you want me to do. I feel like going back to quickly go through the finite square well, and we wrap it up there rather than going forward. Yeah. What do you think? I think you like that. Let's do that. Because what we have forward is almost just what you are going to do next week. Chapter 3, things will be in 3 dimensions. And let me convince you by just flipping maybe 2 seconds per slide. See? It's just stuff in 3D. It's there for you, and we will get back to it. And see the result of the particle in a box in 3D. Not too different from what we had. It's just that instead of just X, Y, we have Y and Z. So not scary at all, just for completion. And that leads to a fancy term called degeneracy. So we just did 1-dimensional harmonic. So this is the 3-dimensional. So I was just making my notes more complete by doing both 1D and then 3D. So nothing big. And here is the last slide telling you to get ready for operator algebra, linear algebra, Dirac notation. Who is dying for this? Yes, yes, I am.
So excited.
This is it.
Hello.
This is that diabolically clever. We're setting it up. We're gonna be diabolically clever.